In this video, we will discuss the class of reactions called cycloadditions and their applications in organic synthesis. After this class, you will be able to identify cycloadditions related to the Diels-Alder reaction. The Diels-Alder reaction itself is an example of a cycloaddition. Two pi systems come together to make a ring. We will explain observations related to cycloadditions with molecular orbital theory, predict the rates of Diels-Alder reactions based on FMO theory. In the last lesson, we made these predictions based on conformational analysis. We'll look at electronics and FMO theory this time. Finally, we will apply cycloaddition reactions in synthetic schemes of organic molecules. Although we were not together face-to-face for the last lesson, often I get some questions, common questions from the Diels-Alder lesson. One of those is, what is the heat for? And oftentimes these reactions are heated, but I mentioned a few times in that lesson, this delta here, this heat really means thermal energy. Thermal energy exists at all temperatures above absolute zero, so it doesn't mean literally hot in the sense of something that will be hot to you, though often these reactions are heated. So we will discuss more about what this means today. A second common question I encounter is, why does there have to be an electron withdrawing group on the dienophile? Or sometimes just, does there have to be an electron withdrawing group on the dienophile? Yes, when the diene is the electron-rich species, there is a requirement for an electron withdrawing group on the dienophile for a fast Diels-Alder reaction. Of course, we did see one example in the previous lesson that perhaps the diene is the electron-poor component, and then the dienophile should be electron-rich. But this is the less common variant of the Diels-Alder reaction. This was called that reverse electron demand. But for the prototypical Diels-Alder reaction, yes, an electron withdrawing group is required on the dienophile for a fast reaction. As far as why, we will discuss that today. So as we address these questions and think more deeply about cycloadditions as a class of reactions, please provide a complete curved arrow mechanism for each of these reactions. So I've just proposed some reactions here, so you should be able to draw curved arrows from starting material to product, and then just predict whether or not each reaction will occur. All right, so in other words, just because I drew it doesn't mean it happens. So provide the curved arrows and then predict, yes or no, do you think it will occur? I will refer to these reactions as A, B, and C. We'll take a look at reaction A now. This lone pair of electrons makes a bond with the ring. Here it is. Now, of course, this is not really a lone pair of electrons. Those electrons are involved in a conjugated pi system. In this resonance structure, though, it certainly looks like a lone pair. The electrons in this pi bond make a bond to the other oxygen on the other end of ozone. And the electrons represented by this pi bond move to oxygen. This transformation would represent a cycloaddition. 2 pi electrons from the alkene react with 4 pi electrons from ozone. We don't know whether or not it occurs. You can certainly make a prediction, but we've drawn the curved arrows for the proposed transformation. In reaction B, 2 alkenes are proposed to come together in a cycloaddition like this. One bond is formed, another bond is formed. So 2 pi bonds are broken, 2 sigma bonds are made. Looks good, right? Making sigma bonds from pi bonds. This would represent 2 pi system adding to a 2 pi electron system. We don't know, but I'm sure we're going to find out. Pretty cool cyclobutane product. Oh, this last reaction C, this looks extremely exciting. Let's draw the curved arrows for that. This is a fully conjugated system, but it does appear that the 6 pi electrons in this part of the system are perhaps reacting with the 4 pi electrons in that system. This question is always very exciting because I've made a typo and year after year I forget to change it. Apologies to you. Apologies to all the years worth of students who have endured this typo. All right, that's better. Let's draw the curved arrows. These pi electrons from the 4 pi system are going to make a bond here. Let's represent that. We're going to have lots of colors. Be very exciting. So 2 pi electrons, this bond. These electrons will move over between these 2 carbons. Here's that bond. That means that these pi electrons will move over. There's that pi bond. And then finally, these pi electrons will make the bond on the other end of this diene. The carbonyl carbon isn't reacting. There it is. The 2 carbons adjacent to it have made those new bonds. We can see the CH2 unit of the diene. There it is. Oh, and one more curved arrow. When this bond is formed right here, those pi electrons in the diene do move over. Apologies for that. Running out of colors, but here we go. So those pi electrons move over and form that bond. Wow, there's no way this reaction happens, right? I don't know. Let's find out. Each of these reactions represents a proposed cycloaddition. Let's return to the one cycloaddition that we know occurs, that is the Diels-Alder reaction, and analyze it with frontier molecular orbital theory. The curved arrow mechanism for the Diels-Alder reaction is as follows. This reaction is facilitated by thermal energy, and the transition state is a cyclic 6-membered 6 pi electron transition state where the electrons are moving in a ring. So this is an example of a pericyclic reaction and yields a cyclohexane product. What are the orbital interactions in the Diels-Alder reaction? Well, there'll be a HOMO and a LUMO, like every other reaction that we have discussed. There will be a filled orbital and an empty orbital. Which species is the nucleophile and which species is the electrophile? To address this question, consider what we have previously discussed regarding the normal electron demand Diels-Alder reaction. Typically, there are electron donating groups on the diene and electron withdrawing groups on the dienophile. Thus, we might expect the diene to act as the nucleophilic species and the dienophile to behave as the electrophilic species. The electron withdrawing group would make this electron poor. The electron donating group would make the dienophile electron rich. Seems like a reasonable expectation, at least for the normal electron demand Diels-Alder reaction. To briefly review frontier molecular orbital theory, aka FMO theory. Imagine that molecules A and B collide in space to make C and D. Each of these reacting species, A and B, has many molecular orbitals. Some of them are filled and some of them are empty. And when these two molecules collide, all of their orbitals interact. All of the orbitals on A overlap with all of the orbitals on B. That is a lot of interactions, and I'm not going to draw them all out, but all of the orbitals overlap. And we certainly cannot model all of those interactions. So to simplify, we consider 3 types of interactions. And for a full lesson on this topic, go back to the beginning of the Organic Chemistry 2 lecture series, or go back to Organic Chemistry 1 at the beginning of that lecture series and review these topics. There are 3 types of orbital interactions that may occur. First, imagine filled. So these 2 orbitals can overlap in space. 2 orbitals overlapping would generate 2 new orbitals. I'll draw out that possibility in just a minute. So that would represent filled. Unfilled, that might be represented by, say, this unfilled orbital in A interacting with this unfilled orbital in B. Finally, filled-unfilled interactions that might be represented by this orbital on A overlapping with that orbital on B. Okay, those are the 3 types of orbital interactions. There could be filled, like this, unfilled, or filled, unfilled. And remember, all of the orbitals are overlapping. We're just trying to figure out which of these interactions is actually useful, which one of these can we use to understand what is going on in the chemical reaction. Well, when these two filled orbitals overlap for molecules A and B, they do create two new molecular orbitals. However, they start out with 4 electrons, they end up with 4 electrons. These 2 electrons are stabilized. They are certainly lower in energy than where they started. However, these 2 electrons are higher in energy than where they started. Thus, there is no net stabilization of electrons when two filled orbitals overlap, and we do not need to consider that type of interaction. Great, so we can narrow down some of the different interactions that we're considering. We do not need to consider all these interactions, many of which I have not drawn, when the filled orbitals overlap. It's not productive. There's no net stabilization of electrons. Next, let's consider unfilled, such as this interaction between an orbital in A and an orbital in B. Keep in mind there are many unfilled interactions that can occur. So that's just one type that we're thinking about here. Do we need to think more carefully about it? Yes or no? All right, when two unfilled orbitals overlap, they do create two new molecular orbitals, but there were no electrons in here to start with, so there's no electrons to put in those new molecular orbitals. So we don't need to consider this type of interaction. No electrons, nothing to stabilize, not a significant type of orbital interaction. Finally, a filled-unfilled interaction, such as this one. When a filled orbital overlaps with an empty orbital, just like when any two orbitals overlap, two new orbitals are created. Two orbitals makes two orbitals. Now there were 2 electrons that we started with. They go into the lowest energy orbital. And eureka, what do we see? Overall, electrons are stabilized. So this filled-unfilled interaction is the significant type of orbital interaction when two molecules combine in space to make new bonds, break old bonds, right? Filled, unfilled, that's significant. Well, there are a lot of filled and a lot of unfilled orbitals. We could imagine that each of these filled orbitals interacts with each of these unfilled orbitals for B. Each of these filled orbitals for A, B interacts with all the unfilled orbitals for A. So can we narrow it down further? Yes, we can, because as it turns out, the interaction between orbitals that are close in energy is more important than interactions between orbitals that are far apart in energy. Orbitals that are closer in energy have better overlap. That means when they make new orbitals, those new orbitals are lowered in energy more than if the two starting orbitals were further apart in energy. And the name of the game is lower energy. The universe is going to lower energy. So because of that, we can understand the reactivity of organic molecules, most of it anyways, by examining only a small number of orbitals, known as the frontier molecular orbitals. These frontier molecular orbitals will be the closest in energy and thus overlap in the most significant way, which just means that their overlap results in the most lowering of the energy of electrons when they move into those new orbitals. All right, so those frontier molecular orbitals are known as the HOMO and the LUMO. The HOMO is the highest energy occupied molecular orbital, so it's filled, it has electrons in it. And the LUMO, the lowest energy unoccupied, so empty molecular orbital. Remember, we're talking about the filled, empty interactions because in those interactions, when the two new molecular orbitals are made, one is lower energy, one is higher energy, the electrons are lowered the most. Electrons are stabilized in this type of interaction. So our model suggests that we only need to consider the HOMO and the LUMO of molecules A and B. There are 2 options. The HOMO, highest energy filled molecular orbital of A, interacts with the LUMO of B. Or the highest energy filled molecular orbital of B interacts with the LUMO of A. These are the only 2 significant interactions between all the orbitals of A and all the orbitals of B. Neither A acts as the electron-rich species as the nucleophile and donates electrons in its highest energy orbital to the lowest energy orbital of B. That would make B the electron-poor species or the electrophile. Or the other way around. B is the electron-rich species. It acts as the nucleophile, donating electrons to A, to its lowest energy empty orbital, making A the electron-poor species and thus the electrophile. Well, which is which? Well, it depends from case to case. In the case of the Diels-Alder, what orbital interaction should we consider? Well, the Diels-Alder reaction is an interaction of pi electrons and pi orbitals. So we can easily simplify our analysis to think about the pi orbitals of the diene and the dienophile. Thus, we should draw the pi molecular orbitals for both of these species, the diene and the dienophile. Really nice review from earlier in the term. Give it a shot here. The diene is a 4-atom pi system. 4 p orbitals make 4 pi molecular orbitals, represented by these 4 orbitals. There are 4 electrons in this pi system. Those 4 electrons will occupy the lowest energy orbitals, psi naught and psi 1. The dienophile, fancy alkene, can be represented by a 2 pi system, so 2 p orbital systems, so pi and pi star are the orbitals. Now, it is more complicated, right? I mean, there's electron withdrawing groups often on the alkene, and they might have p orbitals conjugated to the alkene. So this is a simplification, but when you draw the arrows for the Diels-Alder reaction, you're just showing these 2 pi electrons reacting. So that is why we're just considering the orbitals that would describe a 2-atom pi system. 2 electrons in that system. Those electrons will occupy the lowest energy orbital, which is pi. The antibonding orbital, pi star, is empty. We should identify the HOMO and LUMO for both of these species. For the diene, the highest energy filled molecular orbital is psi 1. The LUMO, the lowest energy empty orbital, is psi 2. For the alkene, the highest energy filled molecular orbital is pi, and the lowest energy unfilled molecular orbital is pi star. So there are 2 possibilities. The HOMO of the diene interacts with the LUMO of the dienophile, or the LUMO of the dienophile reacts with the HOMO of the diene. And actually, for our FMO analysis on the next slide, it does not matter which of these interactions you choose, but I will point out for a normal electron demand Diels-Alder, it is the HOMO of the diene that it is suspected to react with the LUMO of the dienophile. Just think about it, right? The diene typically has electron withdrawing groups on it. It is electron rich. It can be thought of as the nucleophilic species, whereas the dienophile has electron withdrawing groups on it and is electron poor, can be thought of as the electrophilic species. Electrophilic species accept electrons with their LUMOs. Nucleophilic species donate the electrons in their HOMO. So this is the orbital interaction that I will use to demonstrate why this reaction occurs on the next slide, but the argument will be the same no matter which of these combinations you used, and you can prove that to yourself later if you would like. Well, in fact, the Diels-Alder reaction is considered thermally allowed. Wow, that's very specific language. Sounds kind of scary. Yeah, it's scarier when I tell you that this is instead of the alternative is thermally forbidden. So the Diels-Alder reaction is thermally allowed. And given what you've learned, why might that be the case? Recall the cyclic transition state for the Diels-Alder reaction, where the bond between one end of the diene and the 2 carbons of the dienophile is made at the same time as the other bond between the other end of the diene and the other carbon of the dienophile. We can see that the orbitals interact in phase, so shaded lobe and shaded lobe, on both sides, unshaded lobe, between the diene HOMO and the dienophile LUMO. When 2 orbitals overlap in phase, then they may overlap constructively and make a bond. And that is what occurs here, right? Two new sigma bonds are made. For that to happen, the HOMO and the LUMO must overlap in phase on both ends of the diene, where both carbon-carbon bonds are made. When overlap can occur constructively, a reaction is called thermally allowed, or another way to describe it is symmetry allowed. The symmetry of the HOMO and LUMO allow for this reaction to happen. Okay, well, really a better way to explain symmetry allowed is to show you thermally forbidden. So let's do that now. And what we're going to do is revisit these three reactions from the very beginning of the video when I asked you to draw the curved arrows and predict whether or not each reaction would be observed or not. Now, really, you had very little basis upon which to make that prediction. I just kind of wanted you to guess, honestly, and if you had some prior knowledge that helped with that guessing, that's good. If you didn't, that's okay too. So now go back and revisit your predictions for each of these molecules. Given the fact that there is reaction for the first two, they both occur, but there is no reaction for the second one. And then let's try to explain the observed reactivity for each of these cycloadditions with frontier molecular orbital theory. So what we're going to do is we're going to get the HOMO of one of the pi systems, the LUMO of the other pi system, and just see, like we did for the Diels-Alder, is there overlap on both ends to make these two new bonds. If there is, it's allowed. If there is not, it is forbidden or not allowed, and the reaction doesn't occur. So spoiler alert, forbidden. Allowed, allowed. What I would do right now is I would pause, I would redraw in the curved arrows for each transformation and try to draw out the HOMOs and LUMOs.
Reaction A reminds us a lot of the Diels-Alder reaction. There is a 2p orbital system with 2 pi electrons in it, just like a dienophile. Reacting with, this is a 3p orbital system, but it has 4 pi electrons in it. Okay, so you need the HOMO of one and the LUMO of the other, and it does not actually matter which interaction you analyze. So you can analyze either interaction. So this one or this one, and you're going to get the same answer. So don't worry. Don't worry. Just pick the HOMO of one and the LUMO of the other. So here is the LUMO of the 2p orbital system with 2 pi electrons in it. All right, that system looks like this. And now a little bit harder perhaps, there is the 3p orbital system. Now, hopefully you recall how to draw that from much earlier this term. If you do not, that is okay. You will consult those lessons. So 3p orbitals means 3 pi molecular orbitals. First one has no nodes. One node symmetrically distributed like a wave. 2 nodes symmetrically distributed. Yeah, there are 4 pi electrons in that system. We're called the beginning of the lesson, where this looks like a lone pair, but it actually is in the pi system. It is in a p orbital. It's conjugated to the pi system. So there are 4 pi electrons in that system. Here they are. That makes Psi2 the LUMO, the lowest energy empty orbital, and Psi1 the HOMO. Since I've chosen the LUMO of the 2 pi system, I'll choose the HOMO of the 3p orbital system. And I'm just going to demonstrate something because since, I know what this is supposed to look like, and so I make it look like that. But let's say I draw the HOMO of the 3p orbital system like this. And then I want to look for the overlap. And I say, there's no overlap on either side. Okay. Remember, where you put the shaded and the unshaded is totally arbitrary. So if there's no overlap on either sides, that means that you need to reverse the arbitrary shading. So here, make this shaded, and then we're going to change phase across the node. So now this lobe is shaded. And then now what we can see is there's actually constructive overlap on both ends. Okay, so remember that these pi systems interact the bottom of one with the top of the other. So that's why we're looking here to see if the orbitals overlap in phase or out of phase. Okay, good. So if there's overlap on both sides where these new bonds are formed, that means the reaction will be thermally allowed. In the case of reaction B, we can see, I've told you, it's not observed. The reaction is not observed, and it is thermally forbidden. Let's understand why. So we have two p orbital systems with 2 pi electrons, right? 2 pi electrons, 2 pi electrons. So we have two systems like this. So the HOMO of one is going to interact with the LUMO of the other. Filled, unfilled, nucleophile, electrophile. You know this. You've done this all semester. So here's the HOMO, and I'm going to draw the LUMO. Where you draw the shading, of course, is arbitrary. What is not arbitrary is that shading changes across the node. That is what the node means, right? Here's a node. It goes from positive to negative, so the shading needs to change. And what we see is that on one side, there's overlap, but on the other side, there is not overlap. You have unshaded with shaded. They would destructively interfere. They're interacting out of phase. So this reaction, 2 pi electrons plus 2 pi electrons, it is thermally forbidden. Really easy to draw the curved arrows for, right? But it doesn't happen. There is not constructive overlap on both sides where the bonds are supposedly formed. Those bonds would not be formed. A bond could be formed on this side, but on the other side, because the orbitals are combining out of phase, they destructively interfere. A new orbital is not formed and a bond is not formed. Thus, no reaction. No reaction. Now the last example, we said, oh, this looks crazy. There is a 6p orbital, 6 pi electron system interacting now with a 4p orbital, 4 pi electron system, as we discussed at the beginning of the video. We're going to choose the HOMO of one and have it interact with the LUMO of the other, but of course you first need to remember what those orbitals look like. So you can recall that. I'm going to sketch that up at the top of the screen, and it's just going to magically appear in just a moment. All right, magic, here they are. We're just going to pick the HOMO of one and the LUMO of the other. I'm going to choose the HOMO of the diene, and I'll use the LUMO of the triene. But either combination works. So for the diene, the 4p orbital, 4 pi electrons, here are the 4 pi electrons. That makes the HOMO psi 1 and the LUMO psi 2. So drawing out the HOMO of the diene down here at the bottom of the screen. So for the 6 pi electron system, the 6p orbital system, I'll be drawing out the LUMO. So first I just have to remember the orbitals. Then I have to say, okay, there's 6 pi electrons in this system, so that means it looks like this. 2, 4, 6, which makes psi 2 the HOMO and psi 3 the LUMO. So I'm going to draw out psi 3 down at the bottom. And I want to show you the same thing I showed you before. When I try to show the overlap, it's like, they don't overlap on either side. Okay, well that means switch your arbitrary phases because you just need to flip over the whole system and then you'll have overlap. So where I start the phasing is arbitrary again, but then switching across the nodes, that's a requirement. All right, so now we can see actually, so I just kind of flip the whole pi system over. There's overlap on both sides. That means this is symmetry allowed, thermally allowed, and this reaction does happen, which is observed. Now we understand why. The HOMO of one species must overlap constructively with both ends of the LUMO of the other pi system in these cycloaddition reactions. This is a lot. Can we simplify? Yeah, after I made you do all of that, I'm going to help you simplify. We will simplify and state what's referred to as the selection rules. Oh, is there a general rule that we can use to determine whether or not a cycloaddition will occur? Cycloaddition, this is just meaning that 2 pi systems are coming together in this cyclic transition state to generate the cyclic product. Yes, so under thermal conditions, when total number of pi electrons involved in the cycloaddition is equal to 4n plus 2. So for example, the Diels-Alder is thermally allowed. And you see there are 6 pi electrons. 6 pi electrons is an example of 4n plus 2. When that is the case, when there are 4n plus 2 electrons, then it will be thermally allowed. However, when the total number of electrons involved in the cyclic transition state is 4n electrons, like here, the total number of electrons is 4 pi in this 2 plus 2 cycloaddition. We saw it right here. So this was a 4 pi electron. It was thermally forbidden. When the total number of electrons involved in the transition state is 4n, where n is any integer, then the cycloaddition is thermally forbidden. So it will not happen under thermal conditions. And what thermal conditions, so thermally allowed and thermally forbidden. So thermal conditions just means that all the electrons are occupying the ground state. And you might say, well, I mean, aren't all electrons in the ground state? Well, no. No. So an alternative, and if you continue on in chemistry, you'll learn about the fact that you can treat with light. And you kind of already know this, right? Treating with light excites electrons, and then the HOMOs and LUMOs are different, and some of these reactions may occur under photochemical conditions that do not occur under thermal conditions. In fact, this 2 plus 2 cycloaddition can occur under photochemical conditions. It does not under thermal conditions, but it can under photochemical because the HOMOs and LUMOs are different. We're going to stick to thermal conditions today. Now that we have understood why some of these proposed cycloadditions occur and some do not under thermal conditions based on HOMO-LUMO analysis,
let's use FMO theory to understand why a typical dienophile in the Diels-Alder reaction is usually conjugated to an electron withdrawing group. All of these species are excellent dienophiles in the Diels-Alder reaction. An excellent dienophile just means it reacts with a significant rate. Be sure that you can identify the part of each diene that reacts in the Diels-Alder reaction and identify the electron withdrawing group and name all functional groups. The two carbons that look like an alkene represent the reactive part of the dienophile in the Diels-Alder reaction. Those 2 pi electrons from that part of the molecule react with the 4 pi electrons of the diene. However, in each of these cases, the alkene is conjugated, connected to part of a multi-center pi system with the electron withdrawing group. Various electron withdrawing groups are encountered in Diels-Alder reactions. Even nitroalkenes are encountered in Diels-Alder reactions, where this would be the reactive part, and the nitro group is the electron withdrawing group, and you can see that since all of these atoms are sp2 hybridized and adjacent to one another, this is a multi-center pi system. How can we use this analysis to explain why the Diels-Alder proceeds more rapidly, so with a faster rate, if there is an electron withdrawing substituent on the dienophile? Well, let's recall the orbital interaction that takes place in the Diels-Alder. It is an interaction between the highest energy occupied molecular orbital, the filled orbital of the diene, with the lowest energy empty orbital of the dienophile. The diene is acting like the nucleophile, and the dienophile is typically acting as the electrophile. Also recall that the closer in energy the HOMO and LUMO are of the reacting species, the better overlap they will have. So for these two reactions, the Diels-Alder between 1,3-butadiene and acrylonitrile versus the Diels-Alder reaction between 1,3-butadiene and ethylene. The reaction is faster with acrylonitrile, which has an electron withdrawing group. The dienes are the same, so the HOMO for each diene is the same because they're the same molecule. However, the LUMO of the dienophile, when there is an electron withdrawing group, is lower energy than when there is not an electron withdrawing group. Thus, the difference in energy between the HOMO and LUMO of the diene and the dienophile is smaller, resulting in a faster reaction between the diene and acrylonitrile versus the diene and ethylene. If you're wondering how does an electron withdrawing group lower the energy of the LUMO, there's a couple of ways that you can think about that. Those electron withdrawing groups contain electronegative atoms, and electronegative atoms typically have lower energy orbitals than carbon. Also, the electron withdrawing group introduces conjugation, and that conjugation lowers the energy of the pi molecular orbitals, as we have learned. So electron withdrawing groups on the dienophile decreases the energy of the LUMO, resulting in a smaller difference in energy between the HOMO and LUMO of the two reactive species, and ultimately in a faster reaction. I will add to this slide that electron donating groups on the diene would serve to increase the energy of the diene HOMO. Right? We've said oftentimes there's an electron donating group on the diene that actually causes the energy of the HOMO to increase, again resulting in a smaller difference in energy between the HOMO and the LUMO of the two reactive species, and would result in a faster Diels-Alder reaction. So for example, this diene would react faster in the Diels-Alder than just the 1,3-butadiene with the same dienophile because it has an electron donating group and a higher energy HOMO, which makes it a better nucleophile. FMO theory can explain everything, right? Let's pause for a moment and evaluate where we are. So identify cycloadditions related to the Diels-Alder reaction. We are working on that. We have considered these three reactions and understood why two of them are thermally allowed and one of them is thermally forbidden. We will continue to look at cycloadditions that are similar to the Diels-Alder. In particular, reaction A here, we said, is similar to the Diels-Alder because there is a 4-pi electron system reacting with a 2-pi electron system. It's different, though, in that it makes a 5-membered ring, but it is similar in the total number of electrons. And we said that thermally allowed cycloadditions will occur when the total number of pi electrons involved in the transition state is equal to 4n plus 2 electrons, where n can be any integer. Those reactions will be thermally forbidden, like the 2 plus 2 cycloaddition, when the total number of electrons in the transition state is equal to 4n, where again, n is any integer. So we're working on identifying cycloadditions related to Diels-Alder reactions. We explained the different examples using FMO theory. So forbidden versus allowed based on HOMO-LUMO analysis. All right, that was also here. And now we just accomplished this third goal, which is to predict the relative rates of Diels-Alder reactions based on FMO theory. So we learned there will be a faster rate of Diels-Alder reaction when X is an electron withdrawing group. So for example, if X was a nitrile, it would react faster than if it were hydrogen, which is not an electron withdrawing group. And that is because the dienophile would have a lower energy LUMO. We also learned there will be a faster rate of Diels-Alder when the diene contains an electron donating group, because the electron donating group raises the energy of the HOMO of the diene, resulting in a smaller difference in energy between the HOMO of the diene and the LUMO of the dienophile, once again resulting in a faster reaction. Those are two factors based on molecular orbital theory that we have identified that affects the rate of the Diels-Alder reaction. In the previous lesson, we discussed sterics and conformational analysis, particularly related to the S-cis conformation of the diene. How often the diene, or how many molecules of the diene populate the S-cis conformation and how fast the Diels-Alder reaction occurs really will depend on if it's locked in the S-cis versus locked in the S-trans, which would not react. Or if so locked in the S-cis would be good, fast rate. Or if there's some poor steric interaction in the S-cis, this would certainly have a slow rate. You can review that lesson as necessary. So now we know several factors between the two lessons that affect the relative rates of Diels-Alder reactions. And now finally, we want to transition to applying cycloaddition reactions in synthetic schemes. But to do that, we need to learn a few more reactions. The Diels-Alder reaction is not the only cycloaddition that we will use in synthesis. However, before we do that, I very much want to show you an interesting reaction here. Take a look at it. You may recall that cyclobutadiene is the prototypical anti-aromatic compound. It has two 4-pi electrons and a fully cyclic arrangement of p orbitals. This conjugated pi system would contain 4-pi electrons, which equals 4n, where n equals 1, thus would be anti-aromatic and very, very high energy. In fact, it is so high energy that it took chemists many years to actually make it. And finally, they were able to synthesize it under very, very cold conditions in a frozen argon matrix, if you remember. And I don't recall the exact temperature of frozen argon, but let's say 4 Kelvin, so very, very cold. And you may recall they noticed it was behaving more like two isolated pi systems where there were two short bonds and two long bonds than a conjugated system, since that conjugated system would be anti-aromatic. All right, you can review that lesson if you'd like to refresh your memory more on the details of cyclobutadiene. But for our purposes today, let's check out this really interesting reaction. As cyclobutadiene is heated, and by heated, I mean warmed above 4 Kelvin, a very interesting reaction occurs. Cyclobutadiene dimerizes. Two molecules react with one another to form this product. Wow, two fused cyclobutenes. This system looks pretty strange, but you'll notice it is made up of three non-aromatic rings. These are four-membered rings, so certainly they are strained. There is angle strain and torsional strain, but at least they're not anti-aromatic. So can we propose a complete curved arrow mechanism for the dimerization of cyclobutadiene? Yes, we certainly can. Now, it is very, very tempting, and quite often I encounter this first mechanism. For these two pi electrons make this bond, these two pi electrons make this bond. Now, those curved arrows do result in this product. There is a second proposal that I commonly encounter, and it also leads to the observed product. Whereas in the first proposal, there were two pi electrons plus two pi electrons in what is a proposed cycloaddition. In the second proposal, there are four pi electrons in this one molecule of cyclobutadiene. The first two electrons make that bond. These electrons, they react over here to make this bond. And then finally, two more pi electrons slide over. So we can see that one cyclobutadiene is behaving like a diene and the other is behaving like a dienophile or fancy alkene. In other words, 4 pi electrons plus 2 pi electrons in a cycloaddition. Two pi systems coming together to make a ring. Two pi systems coming together to make a ring. So these are both cycloaddition proposals. If both proposals give the desired product, which one is it? Are they both correct? No, only one is allowed. Do not forget that these reactions are occurring under thermal conditions. Now, I know it's not hot, right? It's just above 4 Kelvin, but the energy is coming from thermal energy, even if it's not a lot. So it's thermal energy, it's not light. It's not a photochemical reaction. So in that case, the selection rules apply. And the selection rules said cycloadditions are thermally allowed for 4n plus 2 pi electrons in the transition state. They are thermally forbidden when there are 4n pi electrons in the transition state. So how many electrons proposed in proposal 1? That's 4 pi total, which is 4n. Thus, proposal 1 is thermally forbidden. So this is not the correct answer. For proposal 2, there are 4 plus 2, 6 pi electrons, which corresponds to 4n plus 2, where n equals 1. Thus, this reaction is thermally allowed. And it looks a lot like a Diels-Alder, right? Diene and a dienophile. So proposal 2 explains the dimerization of cyclobutadiene. It does make this highly strained system of 3 fused 4-membered rings, but that's still lower energy than the energy penalty associated with this molecule being anti-aromatic. And really, just for the record, only one new 4-membered ring is being created. As we move now to learning a few more cycloadditions that we can use in synthesis, let's be sure we have addressed the questions that we had regarding the Diels-Alder from the last lesson. Pause. Try to answer this question yourself. What is the heat for? What does the triangle mean in the Diels-Alder? And then answer, why is there often an electron withdrawing group on the dienophile? Although sometimes heat, so heating a temperature that you associate with being hot, so above room temperature, is required to overcome the activation barrier of the Diels-Alder reaction. So definitely delta sometimes just literally means heat. You have to heat the reaction. However, it always means that the electrons in the reactants are in the ground state. So the reacting HOMO and LUMO for the reactants correspond to the ground state. And then when we're analyzing whether or not two pi systems will come together in a cycloaddition, we were looking at the ends of the HOMO and LUMO to see if they overlapped. So we went through this type of analysis here and here for the Diels-Alder reaction because the HOMO and the diene ends, the carbons on the ends have p orbitals with opposite phasing, and so do the orbitals on the ends of the LUMO of the dienophile. So they have the same symmetry, and so they can overlap productively on each end where the bonds are formed. We saw sometimes that is not the case. So in the 2+2 cycloaddition, the HOMO and the LUMO of the alkene have different symmetries. The HOMO has the same phasing on both sides, both ends of the pi system, but the LUMO has different phasing on the ends of the pi system. Okay, so this opposite phasing. So because of that, there was only constructive overlap on one side, destructive on the other. Thus, this reaction was forbidden. The bonds could not be formed. So thermal conditions, again, just means the electrons in the reactants are in their ground states. This is in comparison to what is called photochemical conditions when the electrons have been excited, and then the HOMOs and LUMOs are different. But that's a topic for another class, another time. Now, why are there often electron withdrawing groups on the dienophile for a Diels-Alder? Well, the Diels-Alder reaction is faster when there is an electron withdrawing group on the dienophile since it lowers the energy of the dienophile's LUMO, making the difference in energy between the HOMO of the diene, the highest energy occupied molecular orbital of the diene, and the LUMO of the dienophile smaller. When X is an electron withdrawing group, the energy of this orbital is decreased, say here. So now this difference in energy between the HOMO of the diene and the LUMO of the dienophile is smaller. Smaller difference in energy between the reacting orbitals leads to a faster reaction. We have achieved our first 3 learning goals using FMO theory to more deeply understand the Diels-Alder reaction and related cycloadditions. To reiterate one more time, a cycloaddition involves pi electrons moving in a ring, moving in a cycle in a cyclic fashion to generate a new ring. Okay, in all 3 cases of these proposed cycloadditions, a new ring was formed. This ring in the last product. So new ring, new ring, new ring. And in each case, pi electrons were moving in a ring in the transition state. Now that we understand more details about when cycloadditions are allowed and not allowed, and what affects their rate of reaction, we will learn a few new cycloaddition reactions and apply those and the ones that we already know to the synthesis of organic molecules. So we'll do that in our next video. Once you're ready, let's move on to that.